1. Primordial black holes. Primordial black holes are conjectural and are thought to have originated not long after the Big Bang, which is a significant amount of time before the formation of galaxies and stars. These black holes, in contrast to the majority of black holes, which originate from collapsing stars, were created as a result of high-density fluctuations in the very early cosmos. They may be exceedingly small, with some even being the size of a proton. Nonetheless, they are still tremendously dense, with the bulk of a mountain or more contained within them. There is a widespread belief among scientists that they could be a component of the enigmatic dark matter that permeates the entire cosmos. Primordial black holes continue to be a topic of discussion in contemporary astronomy, even though we have not yet discovered one. Second, stellar mass black holes. Stellar mass black holes are the most commonly known type. They form when a massive star, at least 8 times the mass of the Sun, runs out of fuel and collapses under its own gravity after a supernova explosion. These black holes usually weigh between 5 to 100 solar masses and are about the size of a city, with diameters of just a few kilometers. We detect them by observing how they affect nearby stars or how they consume matter, emitting X-rays in the process. Our own Milky Way galaxy is estimated to contain millions of these invisible giants. 3. Intermediate mass black holes. Intermediate mass black holes fill the gap between stellar mass and supermassive black holes, with masses ranging from 100 to 100,000 solar masses. For decades, their existence was purely theoretical, but in 2020, scientists detected gravitational waves from the merger of 2 black holes that resulted in a new one around 142 solar masses. Solid evidence of an intermediate mass black hole. These may form from repeated collisions in dense star clusters or by accumulating mass over time. They could also be the building blocks that grow into supermassive black holes found at the centers of galaxies. 4. Supermassive black holes. Supermassive black holes are the largest kind and sit at the heart of almost every large galaxy. Their masses range from millions to billions of times that of the Sun. The one at the center of the Milky Way, known as Sagittarius A star, has about 4 million solar masses. Despite their size, they often go unnoticed unless they're actively feeding on matter, which produces energetic outbursts like quasars. Scientists are still unsure how they formed so early in the universe, but theories include the collapse of massive gas clouds or the merging of many smaller black holes. 5. Micro black holes. Micro black holes are purely theoretical and would be incredibly tiny, possibly smaller than atoms. Some theories suggest they could form from high-energy collisions, like those in particle accelerators such as the Large Hadron Collider. These black holes might evaporate almost instantly via Hawking radiation, a concept proposed by physicist Stephen Hawking. If proven, microblack holes would help bridge the gap between quantum mechanics and general relativity. So far, no such black hole has been observed, but their existence could revolutionize our understanding of the universe at the smallest scale. 6. Rotating Kerr black holes. Most black holes rotate, and when they do, they're called Kerr black holes, named after the physicist Roy Kerr, who first described them. These black holes spin due to the angular momentum of the star they originated. A rotating black hole creates a special region around it called the ergosphere, where space and time are dragged around the black hole. In theory, this allows for energy extraction using processes like the Penrose process. Kerr black holes are considered more realistic representations of black holes in the universe, since most stars spin before collapsing. 7. Charged Reissner-Nordstrom black holes. Even though they do not rotate, Reissner-Nordstrom black holes are charged with electricity. Not only do these black holes have 2 event horizons, but their interior structure is much more complicated than that of uncharged black holes. When it comes to the real world, it is highly improbable that black holes would be able to maintain a net charge since they would rapidly attract opposite charges and quickly become neutral. In spite of this, they continue to hold significance in the field of theoretical physics, particularly when it comes to the investigation of the movement of spacetime and electromagnetic fields under severe conditions. As a result of their unusual characteristics, they are useful tools for conducting thought experiments and simulations. 8. Kerr-Newman black holes. Kerr-Newman black holes are the most complex type of black hole described by general relativity. They rotate and also have an electric charge. This means they combine the traits of both Kerr and Reissner-Nordström black holes. They have an event horizon, an ergosphere, and display some of the most intricate space-time geometry ever theorized. Like the others, their existence in nature is doubtful due to the difficulty in maintaining a net charge, but they are essential for exploring the limits of Einstein's equations and possible connections to string theory and other advanced models. 9. Cold black holes. In alternative models of gravity or cosmology, cold black holes are theories that suggest hypothetical answers to the problem of gravity. The surface gravity of these black holes would be zero, according to some ideas. This would indicate that they would not release any Hawking radiation and could theoretically persist for an infinite amount of time. The conventional understanding of thermodynamics in black holes is called into question by these theories. It is possible to gain insight into how black holes might behave under modified gravitational rules or in extra-dimensional frameworks by considering cold black holes, even though cold black holes do not exist in mainstream physics. In order to investigate the more profound aspects of gravity, they are an intriguing area to pursue. 10. White holes. One might think of white holes as the antithesis of black holes. White holes do not permit anything to enter at all, in contrast to black holes, which can ensnare everything that enters them. In its place, they are only capable of expelling matter and energy. It is impossible to find any evidence of them in the natural world. They are theoretical. According to a number of hypotheses, white holes could be connected to black holes through the use of wormholes, or they could be the other side of a black hole in a parallel universe. White holes, despite the fact that they violate known physics in a number of different ways, are included in some quantum gravity theories and are worthy of investigation because of what they might disclose. 11. Naked singularities. A hypothetical place where gravity becomes infinite, but is not concealed by an event horizon, is referred to as a naked singularity. We are unable to observe what is contained within the majority of black holes because the singularity is obscured. A direct observation of the singularity is possible, however, if the event horizon does not occur. Because of this, the norms of general relativity would be violated, particularly the cosmic censorship concept, which asserts that nature will always conceal singularities at all times. The existence of naked singularities has not been established, but if they were to be found, it would require physicists to re-evaluate the fundamental principles upon which our understanding of the universe is based.